So class N, we're going to talk about graphing polynomials. And I've written some stuff on the board. I'm also going to show you on, I don't know, let me show you on the notes on this, on the notes on Canvas. You can definitely look at the notes on Canvas. I'm looking at the completed notes class N1_James. Those are the ones I'm happening to be looking at. But here are some basics. So polynomial is a function where all the powers of x are positive integers or 0. And I'll give you some more examples here in a minute. But here are a couple of examples. So f of x equal to x and f of x equal to 2x minus 3 are polynomials of degree 1, meaning they're linear is another way we say that. So they're first degree polynomials because the highest power of x is 1. These ones, f of x equal to x squared, g of x equal to 2x squared plus x plus 3, and f of x equal to x minus 2 squared plus 3, those are all polynomials of degree 2, also known as quadratic polynomials. And they're degree 2 polynomials because the highest power of x is 2. And all the other powers of x are positive integers or 0. We don't write the x's to the zeros, but they are there. And thirdly, g of x equal to x cubed, f of x equal to x minus 2 cubed plus 1, and h of x equal to x minus 2 times x plus 1 times x minus 3. Those are all polynomials of degree 3, which we often call cubic polynomials. And again, they're polynomials of degree 3 because the highest power of x is 3. Even though it might not look like it, right? If you multiply this out, oh yeah, you're going to get x cubed plus some lower powers of x. Here also, if you multiply that all out, you're going to get x cubed plus something times x squared plus something times x plus some constant term. So sometimes it might look like, right, you have to actually think about, oh, if I multiply this out, what is the highest power of x going to be? But that's an example of a polynomial of degree 3. So these are just some examples of polynomials. We're going to graph things like this today. I do want to note, because it is going to be important, it's usually easiest to graph a polynomial depending on if it's given in the factored form. So I would much rather be faced with graphing something like this, where it's written as all the factors multiplied together, as opposed to something like 2x squared plus x plus 3. Because graphing something like that, I'm going to have to work a little bit harder to find where the x-intercepts are. Whereas graphing something like this, it's really easy to see that, oh yeah, if x is 2, the whole thing is 0, or if x is -1, the whole thing is 0, or if x is positive 3, the whole thing is 0. And that's going to make it much easier to find those x-intercepts. Let me talk a little bit more, just because I want to say a couple more things. So I do want to point out that something like f of x equal to x squared minus 4 times x minus 1 times x plus 3. This is a polynomial of degree, what would the degree here be? What's the highest power of x if you multiply this whole thing out? You can type it in the chat. Or you could not. Definitely, Sophia, 4. Right, so if you multiply this whole thing out, I think, so when I'm multiplying, I'm not actually going to multiply it out, but I'm thinking, okay, if I multiply these things together, if I take the highest power of x in each part, so x squared times x to the first times x to the first, x squared times x to the first times x to the first, you add the powers and you get x to the 4th. So yeah, that's the degree. That's all I really want to say here. I do want to also point out a few things that are not polynomials that we've already seen in our graphing experiences. F of x equal to the square root of x is not a polynomial. Because f of x equal to the square root of x is f of x equal to x to the 1/2. 1/2 is not an integer. In a similar way, f of x equal to 1 over x squared is not a polynomial. You might say, well, James, 1 over x squared, I see, polynomial. I see a positive integer power of x. And you're right, writing it that way, it does look like x is to a positive integer power. But the problem is it's not x to a power, It's 1 over x to a power. And so I have to actually write it as just x in the not denominator, right, in the numerator, I guess. If I rewrite this, this is really f of x equal to x to the negative second. And oh yeah, my power is not positive, it's actually negative. So yeah. And lastly, one other thing I want to say is that g of x equal to 5, which has what kind of graph? If I was going to graph g of x equal to 5, or if you prefer y equal to 5, what kind of line would that be? Is it horizontal or is it vertical? I'm feeling kind of looking at it. It would definitely be a horizontal line. Yeah. And this is a polynomial. It's not a very interesting polynomial, but it is a polynomial. It's a polynomial at what degree? Well, what's the power of x? I don't have any x's, so the power, well, it is linear. So you make a very good point, Alice, that this technically is a linear function, right? It's a linear function, but it's actually not degree 1. It's going to be degree 0 because the power of x is 0. So, but I will concede the fact that yes, technically, right? I said before, you know, degree 1 is linear. Linear can be degree 1 if the power of x is 1, which it is most of the time. But constant functions, where you don't have any x's and you just get a horizontal line, which is linear, are happen to be degree 0. So really, we just look for the highest power of x. Right here, I see 0 x's, so the highest power of x is 0. You could also, although I don't want you to, but you could write it as g of x equal to 5 times x to the 0th power. No one ever writes it this way because it's unnecessary, but this really emphasizes the fact that, oh yeah, it is a polynomial, it's got degree 0. But this is the way you should really write it. And be like, oh yeah, there's 0 x's, so it's a 0-degree polynomial. Here there is, you know, 4 x's multiplied together, so it's a 4th-degree polynomial. Here there is 1 x multiplied by itself, right? So it's the 1st degree. Here there is 2 x's multiplied together, so it's a 2nd degree, and so on and so on. Okay, so I say so much. I try not to say so much, but it is just a word that I've come to rely on to get me from one thing to the next. Then I was talking to my friend about how I should try to say other things. Like, I don't know what. So the other thing I want to say before we get into, that's fine, thanks, appreciate it. The other thing I want to say before we start graphing polynomials is about the end behavior of polynomials. So now I'm going to be hyper aware of it. The polynomials do one of 4 things as we move either way out to the right or way out to the left. They either get really big or really negatively big. That's kind of the only thing that can happen. If you think about, I just very small examples. If you think about it, it's because, well, the x values are getting a lot bigger. So, well, let me just write some examples. So there are 2 things to determine what happens at the ends of a polynomial. And the examples I'm going to keep in mind are going to be x squared and x cubed and negative x squared and negative x cubed. So in fact, let me draw those first. No, let me not draw those first. Let me just draw a little chart I'm going to draw. So there are 2 things. One is the degree, whether it's an even degree or an odd degree polynomial. So the degree can be either even or odd. And the leading coefficient, meaning the coefficient of the highest power of x, can be either positive or negative. It's got to be one of those 4 things. Positive leading coefficient in even degree, positive coefficient in odd degree, negative leading coefficient even degree, negative leading coefficient odd degree. And so when I think about this, so here's what I think of. So if it's an even degree, so like 2 or 4 or 6 or 8, and a positive leading coefficient, I like to think of something like y equal to positive x squared, which has a graph that looks like this. So what I think about is it's up on the left and it's up on the right. Whereas if the positive leading coefficient and an odd degree, like y equal to x cubed, then it's up on the right and down on the left, right? It looks like this. On the other hand, if it's an even degree and it's a negative leading coefficient, like y equal to negative x squared, then it's down on the left and down on the right. And if an odd degree and a negative coefficient, like y equal to negative x cubed, that's going to flip this over, and it's going to be up on the left and down on the right. And so really, when I think about this, it's not always going to look exactly like that. So when I think I have an even degree, in fact, what I really think of is when the degree is even, they're both the same. So it's either both up or both down. So if the positive leading coefficient, they're both up. The negative leading coefficient, they're both down. For an odd degree, I think of them being opposite, one up and one down. If the positive leading coefficient is up on the right, which means it's down on the left. If it's a negative leading coefficient, it's the opposite of that. It's up on the left, down on the right. So that's the way I really think about these end behaviors. And so when I graph a polynomial, I definitely look at the leading coefficient and the degree to see what's going to happen at the ends. So let me actually show you the notes as well, because there's a little bit more on the notes. I'll share my screen for a moment here. Sure. So if you look at the notes here, there's a few more ways to think about it. So with a positive leading coefficient and even degree, you can either say it starts high. So I should say, when we say starts, we mean going from left to right. So from the left to right, it starts high and it ends high. Or you could say it starts in Q2, right, quadrant 2, and it ends in quadrant 1, right? Because I'll remind you guys, hopefully you can see this okay on the board. Right, this is quadrant 1, this is quadrant 2, this is quadrant 3, this is quadrant 4. And then if it's an even degree and a negative leading coefficient, it's flipped over. So it starts low and it ends low. Or it starts down in the third quadrant, right, the lower left quadrant, and it ends in the lower right quadrant, which is quadrant 4. And then for the odd degree things, different things happen, right? So for odd degree, you're always going to be starting and ending differently, right? For even degree, you start and end either both high or both low. For odd degree, you start and end differently. So for a positive leading coefficient, you're going to start low, you're going to end high. Or you're going to start down in the quadrant 3 and end high in quadrant 1. And then for a negative leading coefficient with an odd degree, you're going to start high and end low, or start up in quadrant 2 and end over in quadrant 4. So when I'm graphing something, this is definitely one of the things I consider when I'm going to graph it. But really, so I should say, after that, the rest of this is just examples. So let's do some examples. In fact, I'm going to start off with not the first example there, because I want to point out one way we could totally do this. So I'm going to graph a quadratic, even though we know what's supposed to happen. So let's graph f of x equal to x minus 5 times x plus 1. And I'm going to ignore the vertex, even though normally we would find it. So what's the degree here? The degree is 2. Right? If we multiply it out, we would get x squared plus some lesser powers of x terms. The end behavior, well, I should say that the leading coefficient is positive. Right, I probably should have said that first, right? And how do I know that? Well, if I multiply this out, I know I'm going to get a positive x squared. I'm going to get minus 4x and then minus 5. But the first term is positive x squared. So my leading coefficient is positive. My degree is even. So my end behavior is up on the left and up on the right. That's usually the way I draw it. You can say it also starts in quadrant 2, right? That's the upper left quadrant, and it ends in quadrant 1. And then we're going to talk about the intercepts. So we're always going to have y-intercepts for a polynomial. It's always true. Every polynomial has y-intercepts because they're defined everywhere. So the y-intercept, we're always going to find by setting x equal to 0. If we set x equal to 0, y is going to equal f of 0, which is 0 minus 5 times 0 plus 1, which is negative 5 times positive 1, which is negative 5. And then we can find the x-intercepts by setting each of the factors equal to 0, which is why we want it in the factored form. So the x-intercepts are a little bit more work because there's something else to say about them. So the x-intercepts, we set each factor equal to 0. You don't have to show all this work. I'm showing it because this is the process. So I'm going to set x minus 5 equal to 0, and I'm going to get x equal to 5. I'm going to set x plus 1 equal to 0, and we get x equal to negative 1. Now, there's something else to know about these intercepts, and it's that they come from the factors that we used to see what they were. So x equal to 5 comes from this factor, and I want to point out, this factor is raised to what power? Well, I didn't write anything there, which means the power is what? Yeah, and this one too. So here's the thing. The power of the factor that the intercept came from is important. It's called the multiplicity of the intercept. So this factor, this intercept, I should say, x equal to 5, how is the y-intercept negative 5? Because if I plug in 0 for x, I get 0 minus 5, which is negative 5, times 0 plus 1, which is positive 1, which ends up being negative 5. We can also multiply this out. But if we actually did multiply this out, which you don't have to do here, but you can, you get x squared minus 5x plus x is minus 4x, minus 5 times 1 is minus 5. And then you can see that if you set x equal to 0, you get 0 minus 0 minus 5. But what I want to say here is that the multiplicity being even or odd actually tells us something. So here, x equals 5 has a multiplicity that's 1. And the same is true for x equal to negative 1. Usually I just write m1. I would write m1 for multiplicity of 1. But when the multiplicity is odd, the graph crosses the x-axis at that intercept. So I'm going to try and graph this. I'm going to show you what I mean. Now you already know this because you know what parabolas look like, right? This is a quadratic or a second-degree polynomial, which has a parabolic graph. And we know that, well, we know what the look of that is. So we're going to have x-intercepts at 5 and negative 1. And a y-intercept of negative 5. And we could find the vertex if we really want to. I'm just going to find it. So actually, no, it's fine. The vertex would be when x is positive 2. And if x is 2, y would be negative 9. So it's somewhere down here, just so I can make the graph look nice. But I want to point out, you know how to graph this, right? It's going to look like this. It's going to be like parabola, 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 parabola. Yes, you have to say parabola, parabola, parabola when you graph it. At least I do. It looks maybe a little bit more like this. Here's what I want you all to see. This is the important part. At this x-intercept here and this x-intercept here, the graph crosses the x-axis. And that is very much specifically because, or at least one way we can tell that is by looking at the intercepts and looking at the multiplicities of the factors that they came from. If the multiplicity is odd, you cross. If the multiplicity is even, you bounce off, which I'll show you in the next example. Some people like to do a thing where they look at the number line. I don't think that's specifically necessary. There is, but you could say, right, you could look at the number line of the zeros, which are 5. The zeros are the x-intercepts, which are 5 and negative 1. And see that if you pick a number larger than 5, like 6, this is positive times this is positive, the whole thing is positive. Pick a number between negative 1 and 5, like 0, this is negative and this is positive, and their product is negative. Pick a number like negative 2, this is negative and this is negative, so the product is positive, you can see, oh yeah, right? We're going from being positive, right, above the x-axis to crossing to being negative below the x-axis, and then crossing back to being positive, being above the x-axis. Again, I don't think you need to do this number line thing, but it is one of the things you can do when you're graphing these things. I think you can get all that information from knowing if it's bouncing or crossing. Let me show you another kind of basic parabolic example to really drive home the point. This one's going to be even easier. So let's look at y equal to x minus 2 squared. And I'm just gonna graph it right off the bat before I do all the things, because I want to show you what this looks like. We know this looks like our parent graph, y equals x squared, shifted to which way? Shifted 2 to the right. Right, you're right. You're so right. Exactly, shifted 2 to the right. So it looks like this. Right, that vertex moved over 2 to the right. Now look at this. And again, I could do all the things, right? So the degree, right? The degree is definitely 2. If we multiply this out, it would be x squared minus 4x plus 4. Highest power is 2. We don't really have to multiply it out to see it, but you can. The leading coefficient is also positive. And not that we didn't know it was going to do that, but we can see, oh yeah, that means it's going to have end behavior that's up on the left and up on the right. And again, I'm trying to kind of walk through all the things because this is what I want you to think about, right? I want you to find the end behavior. I want you to find the intercepts and then think about the multiplicities of those intercepts. So the y-intercept, again, we set x equal to 0. When we set x equal to 0, we get y equal to 0 minus 2 squared, which is negative 2 quantity squared, which is positive 4. So I get the 0.04 right there, which maybe isn't quite the scale. That's okay. The x-intercepts, well, again, I get the x-intercepts by setting each factor equal to 0. So my only factor really is x minus 2. I mean, you can set x minus 2 squared equal to 0, but you really want to set x minus 2 equal to 0, which means x equals positive 2. So there's my positive 2, comma 0. That's my x-intercept. And I want to point out that this x-intercept came from this factor, which has what power or multiplicity? The multiplicity is 2, which is even. And when the multiplicity of your x-intercept is even, you bounce off the x-axis instead of crossing through the x-axis. So that means we're going to bounce. You could also do the number line thing here. Say, oh yeah. So again, the way on the number line, we only include the points where it equals 0. So the only place where this is equal to 0 is when x is equal to 2. And then we can see if we pick a number larger than 2, like 3, 3 minus 2 is 1, 1 squared is positive. If we pick a number like negative, I don't know, pick a number like, I don't know, 1, I guess, is not interesting, but fine. Pick 1, 1 minus 2 is negative 1, but negative 1 squared is still positive. So we're bouncing off because we're staying the same on either side, right? We're positive, 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 hit 0, and then we bounce off and stay positive. So that's the idea with the multiplicity here. So we're going to use the multiplicity to see what happens around each x-intercept. Okay, let's graph some more things. So this is really the whole idea. When we graph polynomials, we're going to kind of go step by step. We're going to first find the degree and the leading coefficient, so that we can find the end behavior. Second, we're going to find the y-intercept. Third, we're going to find the x-intercepts, right? Because there could be more than one. There could technically be none. Right? It's definitely possible to have no x-intercepts, like if you have a parabola that's shifted up. So for example, like y equal to x squared plus 4, that wouldn't have any x-intercepts. Because if you try and solve this equal to 0, you're going to get imaginary solutions, right? If you set this equal to 0, x squared equals -4, x is the square root of -4 plus or minus, but the square root of -4 is not a real number. It's 2i, which we don't graph. So this graph would have no x-intercepts, but most of the things we're going to encounter in this section will probably have x-intercepts. So we graph the x-intercepts and we note their multiplicities. Because the multiplicity, if it's odd, tells us to cross the x-axis. And if it's even, we bounce off the x-axis. Yeah, that's really about it. And then sometimes I personally don't, but we can also look at the number line to see if y is positive or negative. Okay, so let's look at an example. Let's look at, what have I got here? Well, f of x equal to x squared times 3 minus x. All right, so I would like everyone to type in the chat, what's the degree of this polynomial? What's the highest power of x if I multiply it out? Awesome, you guys are great. The degree is 3. And what about the leading coefficient? If I multiply this out, is the coefficient of the highest power going to be positive or negative? And you can write a plus or a minus. Good question, James. We could just multiply it out. So I multiply this out, it's 3x squared minus x cubed. Now, it's a little misleading, pun intended, about the leading coefficient, because the leading coefficient doesn't mean the first thing you write. It does if you write it in the standard way, where you have the highest power first, the next highest power next, and so on and so forth. But here, the leading coefficient isn't 3, because I wrote the wrong thing first. The leading coefficient is really -1, right? Because it's the coefficient of x to the highest power that we have. So here our leading coefficient is negative. Yeah, for sure negative. You guys all guessed right. But I just want to point out, right? Like, I don't even really want to multiply it out. So what I'm thinking about is, okay, if I take the highest thing here and the highest thing here, right, which is -x, and I multiply those together, oh, I do get -x cubed as my highest power thing, and that has a -1 for its leading coefficient. So this tells me with an odd degree and a negative leading coefficient that my end behavior is up on the left, down on the right. So I know that's going to happen when I graph this thing. Okay, let's talk about y-intercepts. So the y-intercept, I'm going to get by setting x equal to 0. And I'm going to get y equal to 0 squared times 3 minus 0. 0 times anything is 0, so I get 0. A lot of these examples will have a y-intercept of 0 because it makes it nicer to graph a lot of the time. X-intercepts. So one thing to be aware of is that if y equals 0 as an intercept, it means x equals 0 is also an x-intercept. But we're still going to do it by setting each of these equal to 0. So I'm going to set x squared equal to 0. I'm going to get x equal to 0. I'm going to set 3 minus x equal to 0. And I'm going to get x equal to positive 3. And for x equal to 0, everybody, what's the multiplicity here? X equal to 0 came from this factor. Multiplicity is more than 1. It's even, yeah. In fact, Aaron, that's a good point. I don't really care if it's 2 or 4 or 6 or a million. I just care that it's even. So the multiplicity here is 2, but more importantly, it is even. Right? And it's because the x equals 0 intercept came from the x squared factor, and x squared is to an even power. 3 minus x, on the other hand, came from this factor, which is to an odd power. So the multiplicity is 1, which is odd. So we know that x equals 3, we're going to cross. And the x equals 0, we're going to bounce. And personally, I don't love doing the whole number line thing, but we can. But I usually like to, at this point, just start graphing things. So here's what I see. I have x-intercepts at 0 and 3. And I know my end behavior is up on the left and down on the right. So what's going to happen is, okay, so that's kind of the first point I have. So to the left of that, I have to kind of be coming this way because I have to be up on the left. So I'm going to be up this way. But then when I get to 0, well, instead at 0, I'm going to bounce. So I'm going to come down this way and then I'm going to bounce off. So I'm going to bounce off like this. And then I'm going to come back and I'm going to have to cross through like that. So then I'm going down to the right. So I'm like this, like that. I don't know how high it goes, right? Maybe it goes this high. Maybe it really goes like, maybe it goes that high. We're not able to find that information yet at this stage in our mathematical careers. So just trying to draw so it looks nice. Draw so it looks smooth. The other thing about polynomials is, and these are things we haven't defined yet, but I will tell you anyway, polynomials are continuous. This is true for all polynomials. Polynomials are continuous, which means their graphs have no breaks in them. Unlike the piecewise functions we were talking about last class, right? Those graphs definitely had some breaks in the graphs. Continuous functions have no breaks. And they're also differentiable, which you will definitely learn about when you take calculus. For now, I would encourage you to think of differentiability as just being smooth, like me. No, not like me, I'm just kidding. My wife's like, oh my God, I can't believe you said that in class. So smooth meaning not pointy. Yeah, I know. I'm super funny. Sometimes I'm funny, sometimes I'm not. Okay. But yeah, so differentiable means smooth, not pointy. And the counterexample I would encourage you to think of if you're trying to think of a function that is not differentiable or not smooth is the absolute value function. Like the absolute value function definitely has a pointy point at the bottom of it. Whereas these functions, these polynomials, are very much smooth, right? They're nice and the curves work well. You don't have any like jagged points or anything like that. The more mathematical way of saying that is it doesn't have any cusps, but I like to say pointy points because it's more fun to say pointy points. And that's kind of the gist. So let me show you on the class notes for just 1 second. Right, that here's kind of, so this outline is available on Canvas somewhere. I will try and make sure. You don't have to use this outline, but this is kind of the whole thing, right? You find the degree, coefficient, or end behavior, and then the Y-intercept should be singular. There's only ever one Y-intercept if it's a function. X-intercepts, then we find the multiplicities of them and say whether they bounce or they cross. You can do this number line thing if you want. I didn't here, and then graph it. So that's kind of the whole idea. Let's do one more. Yeah, we'll do one more and then we'll talk about being even or odd. Let's look at this function. F of x is equal to x times x plus 2 times x minus 4 squared. And so if I were to multiply this out, I can see that my degree is x times x squared, which will be x to the 4th. So my degree is 4. And my leading coefficient, well, again, if I multiply those together, x times an x squared would give me a positive x to the fourth, right? Unlike the previous example, which I know I erased, but was y equal to x squared times 3 minus x. When I multiply out the highest x's here, a x squared times a negative x, which gives me a negative x cubed as my leading term, with a negative 1 as the leading coefficient. So, oh, yeah, the kid after continues, yeah, good. You guys are on it. Sorry about that. Thanks. So here the leading coefficient is positive. So when the degree is even, it does the same thing on the other side. And when it's positive, they're both up. So we know that we're going to have an end behavior that is up on the left and up on the right. My y-intercept, if I set x equal to 0, so whenever you have a factor of just x by itself or x to a power by itself, you're always going to get y equal to 0 as your y-intercept because you're going to get 0 times some other stuff that won't matter. So y-intercept is y equal to 0 because it's 0 times 2 times negative 4 squared, which is going to be 0 because 0 times anything is 0. X-intercepts are a little more interesting. We've got, so again, I'm really just going to set each factor equal to 0. X equal to 0 is going to be x equal to 0 with a multiplicity of 1, which means we're going to cross. X plus 2 equal to 0 is going to give me x equal to negative 2 with a multiplicity of 1. And x minus 4 squared equal to 0 is going to give me x equal to 4, or x minus 4 equal to 0, which is x equal to 4, which is going to have a multiplicity of 2. So it's going to bounce there. And that's all the information we really need. So I've got my intercepts of 0, negative 2, and positive 4. I know beyond the intercepts, I'm up on the left and up on the right. So I'm doing something like this and something like this. And then at negative 2, I'm going to go through because the multiplicity is odd. At 0, I'm also going to cross through. And at 4, I'm going to bounce off. So I'm going to come down here like this. I'm going to go through, bounce. And if things are done correctly, you should end up, right, the end behavior should end up making it work correctly. Okay, there are a couple more examples in these completed class notes that I would encourage you all to look at because they're good examples, but really it's just the same kind of stuff over and over again. But I do want to skip ahead to the last couple pages because I do want to talk about being even or odd. And being even or odd has a lot to do with how things reflect across the y-axis or across both axes. So a function has even symmetry, or we say a function is even if f of negative x is equal to f of x. Another way of saying this is there is symmetry across the y-axis. Meaning, if you flip it across the y-axis, it still looks the same, which totally makes sense, right? Because what we're saying, right, when you put a negative sign on the x, you're flipping it across the y-axis. And so you're saying, oh, if I do this and it still is the same, it's got that symmetry. My favorite example of this is the function f of x equal to x squared. Right, you can definitely see, oh yeah, I know that parabola, and it definitely looks like, right, it is split in half or symmetric about the y-axis. But the way we actually show that is to show that f of negative x, which is negative x quantity squared, which is negative x times negative x, well, the negative times the negative is a positive, that's positive x squared, which is just the original function. So that f of negative x is really equal to f of x. And in a similar, but not quite the same way, a function is odd if f of negative x is equal to negative f of x. So what this says here, the way I kind of think about it is if we reflect it across the y-axis, it's the same as reflecting it across the x-axis. Or basically, if you do a horizontal flip, it has the same result as if you did a vertical flip. And so this is called symmetry about the origin. Or if you prefer, people also call it rotational symmetry. Meaning you can either flip the function in each axis, and if you do that, it should look the same, or you can rotate it 180 degrees around the origin. If you do that, it should look the same. My favorite example of this is f of x equal to x cubed. If you think about the graph of x cubed, which I'm not good at drawing, but it looks like this. If you rotate it 180 degrees around the origin, oh yeah, it's going to look the same. Or if you flip it in the y-axis and then in the x-axis, oh yeah, it's going to look the same. But the way we would actually check it is by doing f of negative x, which is negative x quantity cubed, equal to, well, negative x times negative x times negative x is negative overall, x cubed, which is the negative of the function that we started with. So the f of negative x is equal to negative f of x. So that's the idea behind even and odd functions. So the problem is not all of them are easy to graph, but it is easy-ish to check this condition for any function. So let's look at a couple quick examples. So where'd my other red pen go? Oh, wait, it's right there in my pocket. So let's look at, for example, f of x equal to 2x to the 6th minus 3x to the 4th plus 1. I want to check if this is even or if it's odd or if it's neither. And the way we usually check this is starting by check, is it even? So it isn't even. Does f of negative x equal f of x? Well, I'm going to check. So I'm going to find f of negative x. It's going to be 2 times negative x to the 6th minus 3 times negative x to the 4th plus 1. And here's the thing. When you take a negative thing to an even power, it becomes positive, right? Negative 2 squared is positive 4. Negative 3 to the 4th is positive 81. Because when you multiply a negative thing by itself an even number of times, the negatives become positive. So negative x to the 6th is just positive x to the 6th. This is going to be 2 times x to the 6th minus 3 times positive x to the 4th plus 1. And oh, look, that's the same as the original function. So I say, oh, that's equal to f of x, which means it's even. That's how we check if something's even. You plug in negative x for x and you ask yourself, do I get the same thing that I started with? Or the same thing as the original function? Do I have enough room here? Probably. Probably not, actually. Let's check to see if this next function is even or odd or neither. So the next one I've got is, sure, g of x equal to x to the 5th times the square root of x to the 4th plus 9. So let's first ask, is it even? So I'm going to look at g of negative x and see what I get. So I get negative x to the 5th times the square root of negative x to the 4th plus 9. Negative x to an odd power, I will get a negative, right? Because a negative times a negative times a negative times a negative times a negative is negative. So it's negative x to the 5th times the square root of negative x to the 4th is going to be just x to the 4th because it's a negative times a negative times a negative times a negative. It's positive. So let me ask you guys, is negative x to the 5th times the square root of x to the 4th plus 9 the same as the function I started with? No. Big no. So it's not equal to the original function, which means it's not even. So then I ask myself, could it be odd? So to be odd, I have to ask, is g of negative x equal to negative g of x? Well, yeah, it looks like it is, right? Because if I just pull out the negative sign here, g of negative x is equal to negative x to the 5th times the square root of x to the 4th plus 9, which is definitely negative g of x. So usually my process for seeing if a function is even or odd or neither is definitely an option, which we'll see in the next example. I ask myself first, is it even? And if it is, great, I'm done. But then if it's not even, I say, well, okay, I got this thing. If I factor out a -1, is it equal to the negative of the function I started with? Oh, it is. Another way people do this, so I like to do it this way and say g of negative x is equal to this. Some people just like to also say, oh, also we can look at negative g of x is just negative x to the 5th times the square root of x to the 4th plus 9. Oh yeah, that's equal to that, so we're good to go. I don't usually think of it that way, but other people definitely think of it that way. And then let me show you, I think I can squeeze in 2 more quick examples here. I really want to make sure that you do see this. So let's look at the next one. How about this function? How about f of x equal to, what have we got here? 2x to the 5th plus 4x cubed plus 6. So again, the question is even, odd, or neither. So check for even. So I'm looking at f of negative x to be 2 times negative x to the 5th plus 4 times negative x cubed plus 6. Odd powers give us a negative, so it's going to be negative x to the 5th times 2, so negative 2x to the 5th. 4 times negative x cubed is going to be negative 4x cubed plus 6. Does this equal the original function? No. So it's not even. So then I personally like to factor out a minus sign, but you could then ask yourself for the odd part instead, you could say, well, what's negative f of x? Negative f of x is negative all of that. If I distribute the negative sign, I get negative 2x to the 5th plus 4x cubed. Sorry, distribute the minus sign. Negative 2x to the 5th minus 4x cubed minus 6. Is that the same as that? No. The minus sign here and the plus sign here are not matching up. This is not equal to f of negative x. Meaning it's not even and it's not odd, so it's neither. There's only 3 options. A function either has to be even, has to be odd, or has to be neither.